So today we'll quickly review. So we have final exam on Tuesday next week, right? 10 to 12 p.m., right? So yeah. So we'll quickly go over what we have learned, and then the so we will have a final on the whole lectures. Okay, so you have to basically just understand what we have done throughout the course. Okay, so if you have any questions, so I will try to answer. Okay. So if I remember correctly, we after the midterm we had learned about the combinational circuits, right? So not much different. So this is kind of bubble logic optimization using De Morgan's law. So you guys know already well. And the compound gate, how you construct and how you find the logical effort and parasitic effort for all the given circuit, and also you have to also be able to construct any combination logic compound gate for the given logic gate. Okay, so this is NAND gate delay calculation. We had also had a similar question in the midterm, so you guys were able to properly solve to find the delay. You know? So in here we had learned about the special case where the input depending on the input activity, we may depending on the input. So if the depending on the activity, there's just some difference between whether we connect signal to port A or B, right? So the late the signal comes in early, we better drive to the B. That comes late, then we connect that signal. Better to connect that signal to the device that directly connected to output, that is closer to the output. Okay, in that way when we pull down, we don't we kind of we pull down or pull up internal node, right, before actually we drop the output. And also we had learned about the asymmetric gate concept. So most of the student doesn't have such the actual design people. The student doesn't use this kind of a technique. Not sure why, but you guys learned about this idea already, right? So here, by having the non-activity signal like a static signal like a reset, we can increase the pull down here. Series connected device and the parallel connection device is the size is small. So in that case, we can optimize the speed from A to Y, right? So that is kind of a asymmetric gate. You can use this technique in your actual design. Okay. And if you have a different sizing, so you can have a different logical effort. Okay. And also one other technique for the making the same delay from all input to output by having this kind of a symmetric gate construction. So this is also good technique for you to design very well balanced signal propagation delay. If you want to have a same delay from all inputs, mostly that is critical in clock signal generation, something like that. So in that case, you can use this kind of a technique in your actual design. Okay. Here we had to learn about the skewed gate, so that we can move the logic threshold as we want. So high-low skew concept we had learned. Yeah, this is asymmetric skew. So we have derived the best PN ratio for the least average delay. Oh, this is also we had kind of had in the midterm. We have calculated that. Seems like this one is covered in the midterm. Any question? So in the large family, we had also looked at the lots of different logic style, pseudo, MOS, dynamic, path transistor. So you know that the concept of dynamic and also the pseudo MOS in your actual So for any logic, you need to able to find out the logical effort, right? Delay and dynamic logic, how you construct the proper dynamic logic. This is also learned. Domino concept was learned. Differential logic gate, how you construct the pull down, that is also learned. Okay, why you so to make the floating node static, we use the feedback keeper like here. Weak keeper device is one technique for you to use in your actual design. This is very critical. Charge sharing as we go down to find deep submicron device. This is parasitic is also critical. That in okay. Domino, path transistor logic is also popularly used technique because this is also the static signal, right? A static logic. So any internal load is already driven. Safe. This is safe for manufacturing. Okay. This is reliable circuit, so they're very simple compared to the gate multi-level gate design. Okay. So using only one NMOS device, NMOS logic is also sometimes used, but most of the case, this kind of logic style is favorable in the low VTH process. In some process, they provide a very low voltage, so that the voltage degradation is minimized. Let's say, for example, threshold is like 100 millivolt or below, then we may utilize this kind of a technique. So out of 1 volt supply, 100 millivolt drop may not be that critical issue or something like that. So old days, this kind of logic style was adopted in some process where the each device VTH threshold voltage is very minimized. Mm. So it depends on your situation. Okay. CPL is also MOS only logic style. Okay. But you have a keeper device in cross-coupled fashion. Okay. So for you, and then we learned about the sequential logic gates. So in this chapter, we have to understand how we calculate the timing. The timing calculation seems like straightforward. This is how we construct the latch and flip flop. So this will you guys probably well know. You guys know well about this. So most of the case is the how we design, how we calculate the timing information timing. So flip flop has a meta stability. There's some window it can run right properly, something like that. The data must be stable around the clock edge. So before the stable time before the clock edge is the setup time, and after the clock edge is hold time. So in this window, the data cannot change for safe operation. Okay, so this concept was explained. Okay, and then for sequencing. So flip flop to flip flop. This is typically most of the design we are facing. So nowadays we usually don't use this kind of latch based design because nowadays all the digital is synthesized by the CAD tool. So CAD tool delay calculation done can be easily done on this kind of a flip flop to flip flop data path, because the timing requirement is straightforward. For the setup time, so clock to Q delay plus logic combination logic delay and setup time of the flip flop, all these three terms must be below 1 cycle, right? Latch based logic, it is very complicated because you guys learned about the time borrowing concept, right? Even though the combination logic doesn't complete within like a half cycle in each clock phase, you can still move on to you can continue its logic calculation on the next half cycle. So we can borrow the time from the next half cycle, but the other cycle, clock cycle side, we kind of lose the timing for other following logic calculation. So to take into account such kind of a time borrowing, the CAD tool is not efficient or not accurate enough to consider all the different cases, because you have to know the all the timing information nearby the logic condition, logic delay, and also the clock phase information. So for this kind of clocking, so clock flip flop to flip flop is kind of a widely used concept. And long time ago, so the post latch is also used in the research area. This is also difficult to properly analyze the timing in the CAD tool in digital. the digital synthesis tool need to properly calculate, but calculate the timing margin, but difficult. So nowadays most of the digital design is based on the flip-flop. The flip-flop, this kind of a simple structure. Okay, we had learned about the concept on the propagation delay, contamination delay, and also all these kind of variable definition. So important thing that out of here, so we have to calculate both worst case and best case delay. For the worst case propagation delay, we care about the setup time violation. Right? Data must arrive before the rising edge. For the contamination delay, we care about the best case delay. So if the data, if the propagation delay is too short, so it may violate the hold time requirement. Hold time requirement is the input must be stable even after, right, clock rising edge happen. So there is some period. So if the delayed combination logic delay is too fast, then this edge will move to the left. So it may fall into the hold time region. So it caused the hold time violation. So this kind of a stable window, as we described it here, so actually this kind of a setup time and hold time window here is kind of depending on the flip-flop implementation, I mean logic style. Most of the flip-flop, so in this lecture we show the similar. In this lecture, kind of a T setup is positive value like 100 picosecond, hold time like 50 picosecond. This is most of the case, but in special flip-flop like a sense amplifier based flip-flop, the setup time requirement is like if you find out the setup time, that even can become minus value like a minus 50 picosecond. So this kind of window can move to the shift to the right. So this this kind of a window location is depending on the actual your flip-flop type implementation. Okay. So max delay calculation is straightforward, right? So you have to be able to calculate properly here. And the latch, I'm gonna move. This is something not as straightforward, but you can take a look at the things. So here in this case, we assume that the input data kind of changes just clock edge happen. But if the time borrowing happens, then actual propagation can complete like even after. So which in this here in this case we assume that the data must complete within one cycle. This kind of the thing was assumed. So we calculated the delay from the input data transition to next cycle, the same location of the input transition. So that is totally one clock cycle. But if the time borrowing happens, then this edge can move to the right, meaning this incoming data transition can be happen in between anywhere where phi2 is active, phi1 is active, right? So this input can be delayed. If the next cycle logic, all the logic remaining propagation delay is short, like it can reduce before this case, then we can use the time borrowing. Okay. So this is the post latch case. Just simplify the flip flop. We use the simple latch. Now we need to understand the minimum delay requirement, that is the whole time violation. So this combination logic delay must be the minimum delay must be properly calculated. The concept you have to understand. Okay. There's a two-phase clocking can reduce the whole time violation requirement. So you guys need to understand. So time borrowing. This is just calculating example, so you can take a look at. Okay, any question? No? This material was not covered on the lecture. 맞죠? 종원? 수업에서 이거 다뤘었나?
안 한 것 같습니다.
예. So this is actually we had not enough time to cover this. This slide is for the all different types of flip-flop implementation. So this is starting from dynamic latch type based flip-flop. So it eliminated feedback inverter type. So this will just for your reference. This will not be on the exam, but if you are interested, then you can take a look at the all other different types of a flip-flop. This is dynamic latch-based flip-flop. This is a C-square logic-based flip-flop, and in very high speed, you can use this kind of C-square-based latch. This is very robust to the clock skew between phi and phi bar. So unlike the previous the design, so this is one benefit. So true single phase latch and flip flop which also can be used. The true single phase means that in the conventional flip flop we have a phi and clock bar. The clock signal and each inversion is always required to reduce the clock buffer power. So only single phase clock is used for flip flop. This is based on the dynamic latch operation. So this is MMOS type and PMOS type latch, and we put both together in between. We can construct master and slave master latch and slave latch, and then we can put some logic in between. This is some other example. So this is just some optimized flip-flop true single phase clocking flip-flop. So if you look at here, only one phase clock is shown here, required. So this is very simple. How many flip-flop? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 flip-flop. Very simplified. This is very fast, high-speed operation you may use in like your frequency divider. You guys, in your homework, you design the frequency dividers. In such kind of a high-speed operation, you may consider this kind of a true single-phase flip-flop implementation. This is all custom design, so you have to design by your hand and layout. This is not provided by the CAD standard cell as a standard cell in CAD tool, because this is dynamic circuit. The dynamic is there's some floating nodes internally. So it is very difficult to guarantee its proper operation in very slow clock speed because of the leakage, right? So this is kind of circuit is only carefully used in high frequency where the clock speed is very fast, so that the leakage is not a problem. Okay. So this, and I just mentioned like a sense amplifier based flip flop shown here. This kind of the first latch and SR, this is a NAND based SR latch. Master latch and slave latch is kind of a construction. This kind of sense amplifier is kind of widely used in the memory design, memory amplifier. To read out the memory value, this kind of a sense amplifier is used. The benefit is that the input is differential and even the very small voltage can be captured. For example, like only like a 20 millivolt or 10 millivolt input difference can be amplified in the front end and then detect that as logic 1 or 0, something like that. So this kind of can be useful in the memory design. So in memory cell, the output voltage development on the bit line is very small because of the large parasitic. So this can be kind of a circuit technique to overcome the limitation. Schmidt trigger is like that zone. So you can take a look at if you want all different types of flip-flop structure. The arithmetic. This is also not covered. We have this is more in detail in arithmetic, so we have not sure. 종원 이것도 안 다뤘지 앞에는, 그죠? 종원?
네.
This is just a brief overview on the two's complement number system. I just brief 이 two's complement는 했었나? 우리가? Have you? Touch
네.
Okay. This is the same concept, just different context. Maybe this slide was recorded and this was covered, right? 그죠?
네.
Adder, just simple adder was kind of covered. In old designs we had, in digital design we had very try to develop new very fast adder structure, like a in the old days, like we more care about the CPU clocking speed, like a 1 gigahertz CPU, 2 gigahertz CPU, something like that. So we competed each other to get the fastest, world fastest CPU. But nowadays the clock speed is not that important. Rather, we put more, rather than this clock speed, we put more core. So we use parallelism. So multi-core process and CPU was used. So the low power and mobile application is more critical. So nowadays, most of the company rely on the like a synthesis tool, where just simple this kind of a full adder structure is used in their full adder. So this full adder cell is just used, full adder and half adder cell, basic cell is used and construct just the adder. So, and also CAD tool internally they provide some different style of adder IP. So we the synthesis optimizer select fastest adder type for the given application. So So there's not much chance of designing adder structure for your design process. So I prefer not to cover that much detail on adder implementation. We just understood what is the concept of a half adder and a full adder and how we construct the such logic style. So using GCPL or CMOS static logic implementation. Once that is available, then we can construct the carry ripple carry adder, something like that. Just straightforward, right? And then for the subtraction, we just where no, this is not the subtraction. This is some optimization to make it faster. In the carry propagation path, we reduce the number of logic gate to make it fast. And also so you guys need to understand for the subtraction how we convert this subtraction. So here is adder. 종원, if you want to convert this ripple carry adder to a subtractor, if you want to do the subtraction, how you convert this logic? 빼기를 하려면 어떻게 해야 돼요?
모르겠습니다.
모르겠어요? 빼기 하는 법을 안 is there anyone who can use the
그냥
convert this to subtractor?
B를 그냥 투스 컴플리먼트로 바꿔주면 될 것 같습니다.
그러죠? B를 two's complement로 어떻게 바꿔줘요? How you convert the B to two's complement? B를 그냥 inversion first invert the B, right? 그죠? invert the B 하고 and we need to add 1, right? invert the B and add 1. How we add 1 here? LSB 1B. 어디다가 1을 더하면 돼요? How we add? 세진? 세진이가 대답한 거지?
네, 맞습니다.
예. 1을 어디다 넣어요? 여기다 뭐 또 do we have to put an additional ripple carry adder to make it a subtractor? 우리가 쓰지 않는 available한 input port is here.
캐리 C인에 넣어줘.
C in here. If we assign that to 1 and then invert the B, then it becomes the two's complement subtractor. For the adder, so we add the C in to 0 and this structure. So this is kind of a universal structure. We can easily convert that to adder and subtractor. Okay? 종원, 알겠어? 머리는?
네.
네. This is just optimizing concept, and this is carry different carry look ahead adder. This carry look ahead adder concept is pre-calculate, generate, and propagate intermediate signal and use that. But you may take a look at if you have time. I would not focus that much on the other style of adder. Carry skip adder or carry select adder is a very straightforward concept. Pre-calculate the this is carry skip adder through the pre-calculate the propagation condition and select the carry, right? Whether the carry is propagate and we propagate first. so that we cut down the carry propagation delay. Okay, so I'm gonna skip all. Simple to understand in the carry select adder, we just calculate two cases for carry in 0 and 1, and then later on we, based on the actual carry input, we select the which one we propagate. This is kind of a very massive the 2x adder cell there, right? So, but it can be fast if you properly design. Okay, I'm gonna skip the question. No, I'm gonna skip all these things. Data pass all zero. This is kind of example of how we design the logic for special case all zero detector and all one detector equality and magnitude comparison. Straightforward, right? All one, all zero is logic, and equality is based on the XOR, right? XOR, XNOR. Magnitude comparator here just based on the subtractor. This is subtract b minus a. Yeah, we have a is all inverted, right? And the LSB is assigned to 1. 1 is assigned to the carrying. So this is subtractor. And then look at the here either 0 or 0, so equality, and also look at the magnitude, the sign bit, sign and 0 to find out magnitude comparison. Okay. And the signed and unsigned operation is just also very critical in actual design. In signed comparison, if the input is, so we can, in this example, we just assume that all the input is 2's complement. Right? For example, this is 4-bit comparator. So range, this in this case, range of the inputs. For example, 4-bit, Jongwon. For the 4-bit, what is the range of the signal? Signal range. What is the minimum value for the out of a 4-bit representation in 2's complement?
마이너스 8이요.
그렇죠? 마이너스 8. What is the maximum?
7이요.
그죠? 네. So 2's complement value, the minimum and maximum is defined like that. But if you consider that input as 2's complement, not the 2's complement, like unsigned value, then what happened? Then what is the minimum and maximum?
(0에서 15요)
Alright, so this is very straightforward. Now what happened if you have a 2's complement adder, 4-bit adder, right? If you have a 4-bit coming in, we want to add that, right? What is the maximum and minimum value? 뭐죠? In that case. So you're trying to add two 2's complement number, for example, right? 뭐예요? 두 개의 2's complement number를 더했을 때 최소와 최대는 뭐예요? What is the value? 예? 그래? 아까 너 얘기 했잖아. 4bit은 minimum minus 8. maximum is 7. So if you add those two, the minimum is minus 16, right? Maximum must be 14, right? Maximum case and minimum case of 2. 그죠? 맞아요? 종원? Is that right?
네.
맞죠? Now the question is, can we represent such case in 4-bit? Can you represent the 4-bit using the 4-bit? Can you represent 14 plus 14? Is that possible? No, right? It's not possible, right? 종원, 무슨 말인지 알아?
네.
So the 4-bit cannot represent the 14, right? So either when you want to preserve the output range, when you want to keep the range, output range, what you have to do is that when you add 2's complement number, how we do 4-bit. 어떻게 해야 돼? What you have to do if you wanna add 4-bit, 어떻게 해야 돼요? How you do? You have to extend the bit to the 5-bit, right? 맞아요? So how you extend the 4-bit 2's complement number into 5-bit? Do you know? 모르나? 준용. For example, 준용 있지?
네네.
The 4-bit number, this is minus 8, right? In decimal. How we convert that 4-bit to 5-bit? 5bit으로 어떻게 represent 해야 돼? 마이너스 8을. 아, 몰라요? 준용? 몰라요?
잘 모르겠어요.
아, 몰라요? 투스 컴플리먼트 넘버 디지털 디자인에서 잘 안 배웠나 보네. 디지털 디자인에서 투스 컴플리먼트 옛날에 안 배웠어요? 컨셉에 대해서? 컨셉과 어떻게 활용하는지 안 배웠나 보네. 심준호 학생은 알아요? Do you know? 준호 심?
제일 앞에 있는 비트 그대로
그죠? 사인 익스텐션 하면 되죠? 사인 익스텐션. 뭐다? 1000에서 여기 사인을 그냥 1 리피트. 그럼 얘는 또 8이 마이너스 8이다 이거. 예? 만약에 5bit, 만약에 4bit 7이 있다. 7이 있어요. 그럼 5bit 7로 만들려면 how we do? Just repeat the sign. Sign is 0, so 0, 0, 1, 1, 1. Right? So we have to use the sign extension. So if you want to add the 2's complement 4-bit, you have to extend this sign 4-bit, add the sign, right? 1-bit sign. So you have to extend the sign. That becomes what? 5-bit 되겠죠? 5-bit. That goes to adder. Then final output 5. So now you can represent where minus 16 to 14, right? So this is the kind of two's complement adder, right? 사인 익스텐션은 쉽죠? 그냥 MSB로 그냥 위에다 붙이면 되는 거잖아요. So simple. But what if you cannot, if you wanna just limit the output, just 4-bit, you want to have the 4-bit, then we have to limit this 4-bit to 5-bit to 4-bit. right? And then there should be no input to overflow or underflow. We have to able to detect the case like overflow, and underflow by monitoring the result, right? 그래야겠죠? This is something required for logic arithmetic logic calculation. Now the question is how we detect such kind of underflow and overflow case. Those are explained somewhere? No? 여기 하지 않았나? 어디 있나? 시프트 없나? 아니, 네? 없나? Here, so overflow case input had what is this? 이게 무슨 의미지? Output sign not equal to B? Okay, this is something. So carry out, we have the value 0, logic we generated 0. Negative is we can look at the MSB of the result. Overflow input had a different sign. In this case it's just special case. We just calculating B minus A case. So if this overflow happen, output sign is different from B, because if in this case, you know what? So this case we assume that input is unsigned. That's why we signed. For signed harder. So this is just for unsigned operation. If the output sign is different from B, so it may fall into the overflow or underflow case, right? Input had a different sign means input have different sign, and then output it. So if you have the different, wait a second, this is signed operation. So input had a different sign. Yeah. So here in this case, input is a different sign, then we added value. So originally B was positive and A is negative, and then subtracted, but output is like a different. The sign is becomes negative, then it becomes positive. In the other case, B started with the negative value and A is positive, then subtracted too much, so the result sign is positive, different from B, then it becomes overflow and underflow. Okay, this is the condition. So we can have a logic to detect this kind of the condition. Okay, the shifter implementation, how we shift. This is the simple shifter logic here. Just copy the value and then select the value to make that simple shifter. Okay. Some shifting operation definition shown in here. This is how we actually design the shifter. Carry save adder is also another style of adder. This carry save adder is kind of widely used in multiplier design. So actual multiplier, we generate many partial product. We have to add them all, right? In that case, we use the carry save. There's the multiplier, how we do the multiplier operation, and what? And also we learned about the boost encoding, right? So you have to understand this. Very simple, very nice concept, clever concept to minimize the partial product. Okay. This is sign the multiplication case. Here sign extension. This is some technique is used. Inverted sign and it'll added one that this kind of operation can minimize like this kind of thing. So signed operation, we can cut down this kind of this area value. So only this can be added. This is a very clever idea to minimize the hardware complexity. Okay. Any question? No? Spent too much on this. And we also learned about the memory structure. SRAM, different kind of memory was used, understood, and memory design. So this is very widely used, kind of SRAM design and layout, decoder. So we just explain that. I'm gonna skip multi-port SRAM concept and the DRAM concept was explained in shift register. Okay, and the CAM ROM PLA. Content XX memory. This is this. The concept was explained, right? There's some comparison operation inside the memory cell. This is required. Did I? ODS engage right unit. Network switch. Inside the network switch, you have the what? The IP address. You provide the IP address, and then you have to quickly for the switch. You have to quickly find out which port I need to transfer the data. Such kind of information must be quickly found based on the IP address that I receive. So in each IP address, we assign that the directed port information. So to do that, we have to constantly find out which port information is stored onto the memory, and then depending on the IP. So we provide the IP and then try to find throughout this CAM array. So once that matched, we spit out the number information and then use that to quickly switch the data, right? So this is a very widely used concept. And flash memory, EPROM, flash memory, ROM structure, erasable structure was used and explained, right? This kind of a floating gate is used for your flash device. ROM implementation. Okay. Design for manufacturing. So this is kind of I will already covered non-ideal characteristic of the device and how we deal with that. This is something that you have to be known. The last, and we just looked at the how we when you design circuit, when you look at the circuit, so you have to quickly be able to identify issue and how we overcome something like that. Some practice was kind of studied. I'm gonna stop here. Any question from there? Any question 없어요? 여기까지 해서 시험을 보면 되겠네요. I have covered briefly on what we have learned. Question? 없죠? question이 없으면 오늘은 여기서 끝내도록 하죠. We'll stop here and we'll see you on Tuesday 10 a.m. Okay. 여러분 바이바이. 수고 많았습니다.
혹시 이번 시간에
네?
계산기 필요하요?
뭐라고요?
계산기
예, bring your calculator as always.
알겠습니다.
네.